when a process is going to be executed, it must be in the CPU. That is for sure. When a process, suppose this is a process P1 and it is going to be executed. So it must be assigned to the CPU at any cost. So when a CPU is called for that particular process, it should be in the main memory. Our CPU this is our main memory, and the CPU or our main memory is divided into frames. Each and every blocks of the main memory is called frames, and sometimes it already happens that if a process, size of a process is larger than the main memory, maybe it happens most of the time, then what will operating system do? Operating system dividing this process into pages. The blocks of the process is called page, and the blocks of the main memory is called frames. So process is divided into pages, main memory is divided into frames, and when it is going to be executed, it is called by the main memory. So main memory, to put all the process into the main memory, we can put one of the pages of the process to the main memory rather than putting all the full processes to the main memory, because our size of the main memory is limited, we know that. And when the main memory called, suppose this pages is divided into P1, P2, P3, P4, there are 4 pages in one process, suppose, and when main memory request any page among these pages, suppose main memory request this page P3, it calling for page P3, then that pages should assign to the CPU at that moment at any cost. This is called demand paging. We know that this is called demand paging. When the main memory is call or request for a pages, that means this is called demand pages. Main memory demands some page, and if that page is not available in the main memory, then we call it as page fault. So this is called page fault. If that demand paging, that demanding pages or requesting pages is not available in the main memory, then there would be a page fault, and if page fault is occur, the main memory request to the secondary memory, and the process who resides in the secondary memory, it is searching in the secondary memory, and in secondary memory it assigned to the process to the main memory. Again, replacement algorithm is there. So if I say that if the main memory size is limited, we know, and if I say the size of the main memory, if I increase this main memory size, and if I ask you what would be the page fault, would the page fault would decrease or increase? So if I say that if I increase the size of the main memory, then the page fault is decrease or increase. What would be your answer? Obvious answer is page fault would decrease, because if the size of the main memory would increase, then more and more process would resides in the main memory, and there will be no chance of page fault and no replacement of the pages. So when the size of the main memory is increased, page fault will decrease. So the graph, maybe the diagram or the graph, if I draw like this, here I took frames of main memory, and in this side I took just pages or page fault. This side I took page fault, and this side I took frames of main memory. Okay, here are suppose our main memory is divided into 4 or 5 frames like this. Okay, when the frame is 1, at the frame number 1, obviously the page fault, the number of page fault at this frames would high, obviously very high, and when the frame is increased to 2, then the page fault would again a little lower, and again when the page frames of main memory is again increased, the page fault would decrease, because this is the obvious case, right? The number of when the sizes of the frame is increased, the page fault would decrease. So our graph obviously would be this type of graph. Fine, because the page fault would decrease when the frames are increased. Okay, this is the graphs of frames of main memory and page fault. But in some cases it may happen when the frames of the main memory is increased, sometimes the page fault also would increase. Okay, or you can say the page fault is increased with the increasing of the frames of the main memory. Obviously that is the abnormal cases, because we know frames of the main memory when increase, page fault would decrease, should be decreased. But in some cases increasing of frames of main memory, that would decreasing of rather than decreasing of page fault, it would increase. It would increase by like this. So this is obviously an abnormal conditions. It should not be that. So that condition is called Belady anomaly, and this Belady anomaly is occur in always in fast in fast out FIFO page replacement algorithm. Fine. So what is this Belady anomaly? The Belady anomaly is the number of page faults would increase with increasing of the frames of the main memory. Okay. So let us see how the Belady anomaly is occur in FIFO page replacement algorithm. I will take examples, and by that algorithm, by that FIFO page replacement algorithm, we will check how the page fault is increased. Okay, let's see. So I have taken 2 examples here, and I am doing this algorithm using FIFO page replacement. So first examples, we have taken 3 frames, and the second examples we have taken 4 frames. So we have increased the frame size in the second examples, and as the rules, as always, the increasing of the frames, the page fault of this example should higher than this type of examples. Okay. So obviously this is the second example, second number algorithm, and this is the first number algorithm. So as the page frames are increased, the page fault of 2 diagram obviously decreased as compared to 1 diagram. So let's see and let's solve this algorithm. So there is obviously page fault, 5 is not there, so 5, now 5, next 4 is not there, there is also a page fault, fine, so 5, 4, again page fault, 5, 4, 3, now the frame is full. Okay, so next page has to be replaced. Which page? According to FIFO, we took the oldest page. Okay, so 5, 4, 3. Here 5 would replaced by 2. 4, 3. Here also it is a page fault, and again page fault. Okay, so 2 is recently used, and 4 and 3. 4 would replaced by 1. Fine. Again 4 is not there, there also a page fault, again 2, 1, 3, so 3 is oldest, so 4 is replaced by 3, again page fault, 2, 1, 4, 4 is newly coming page, so 2 is replaced by 3, 1, 4, again page fault, 5 is not there, So 1 is replaced by 5, 3, 5, 4. Okay, now 4 is there in the main memory, so there is a hit, 3, 5, 4. Again hit, 3 is there in the main memory, so 3, 5, 4. Again page fault, so 3, 5, 4. This 4 is replaced by 2, 3, 5, 2. Again page fault, so 3, 5 and 4. So 4 is again 3, here is 5 and 2 is recently used. So we replace 3 to the 1, 5, 2. And finally this is a hit because 5 is there in the main memory, 1, 5, 2. So count down the page fault. So page fault number of page fault 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So page fault number is 10 and hit ratio, so count down number of hit 1, 2, 3. So hit ratio is 3 by 13 and this was page fault ratio 10 by 13. Fine. So next solve this this type of algorithm where we increase the frame size. Okay. So another frame is adding to the main memory. So first is 5, there is a page fault, again there is a page fault 5, 4, again another page fault 5, 4, 3 and again 5, 4, 3, 2, again 1 would be replaced. So again here is page fault. So 1 is replaced. So according to FIFO we replace this 5 to 1, 1, 4, 3, 2. Again there is a hit. So 1, 4, 3, 2. Again there is a hit, 3 is there, then 1, 4, 3, 2. Again page fault, so we took 1, 4, 3, 2. So obviously 4 is replaced by 5, 1, 5, 3, 2. Again page fault, so we replace the oldest one, 1, 5 is recently used and 3 and 2. So 3 is replaced by 4, 1, 5, 4, 2. Again page fault, so 3 is replaced by, see, 1, 5, 4 and 2. So 2 is replaced by 3, 1, 5, 4, 3. Again there is a page fault, so 2 is replaced by here 5, 4 and 3. 2 is replaced by 1, 5, 4, 3. Again there is a page fault, so here is 2, 5, 4, 3. So 5 is oldest one, so 2, 1, 4, 3. So again there is a page fault, so 5 is replaced by here 2, 1 is recently used, 4 and 3. 4 is replaced by 5, 2, 1, 5, 3. So count down in the second diagram, count down the page fault. The number of page fault equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And hit ratio, hit mark is 1, 2, here is 2, 13 and this one 2 by 13. So see, compare this two algorithm. We just apply FIFO page replacement with both of the algorithm, and also we increase in the second algorithm, we increase the frame size. So obvious things is, if a page fault is increased or decreased, if a page fault is decreased, then the frame size also increase. That is the obvious, your obvious answer would be what? The number of frames of a main memory increased, then the page fault is also increased. But in some condition like this, the page fault, here is frame is 3 and here the number of frames is 4. it should be decreased, page fault should be decreased, but here the page fault number is 10 and here the page fault number is 11. Okay, so this condition is called Belady anomaly condition, and it also occur in FIFO page replacement, not in LRU or optimal page replacement algorithm. See here at this examples, why this occur in FIFO page replacement. The main disadvantage is we always replace the active page. Okay, that's why page fault is increased. Okay, like this here 5 is used, again at the point of 5, at the place of 5 2 is replaced. Now again 2 is replaced. Okay, 2 4 3 is the page, then again the again 1 is replaced by 4. Okay, again and again here 1 4 is not there, again at the place of 3 we replaced 4 again, and again 3 is not there, so again we replaced at the place of 2 we replaced 3. Again here is a page fault, so we replaced again and again the active page. When the page is recently come, we replace again to that page, so page fault would increase in this Belady's anomaly algorithms. Okay, so next is MRU page replacement algorithm. What is this MRU? MRU means most recently used. That means most recently used. Suppose I took the same example like this. Like this, we took the pages, this is the reference string or pages, and this is the main memory, and we just solve this algorithm by most recently used. So let's solve this. See, most recently used mean in LRU we took the least recently used, or the pages which has not been used for the longest amount of time. In optimal, which will not be used for the longest amount of time, futuristic approach, we took the futuristic approach. But in MRU we replace the page which just recently used, like this. Here this is a page fault, again there is a page fault, again there is a page fault, again here the main memory is full. Now we have to replace the recently used, the page which will be replaced, which will be swapping into the main memory, this 2. So we traverse from this side, not this type, this is the futuristic, this is the optimal page replacement, and here we just traverse to the recently used. Which number is the recently used? This 3 is recently used, the 3 is just side of the 2. So we just replace among 5 4 3, which number is recently used, which is just aside to the 2 3, we replace this 2 to 3, 5 4 again. So there is a page fault, again 1 is not there, among 5 4 2, which is recently used, 2 is obviously recently used, so 5 4 1, again 4 is there, so there is a hit, 5 4 1, 3 is not there, there is page fault, among 5 4 1, 4 is recently used to the side of 3, so 3 is replaced. Okay, again 5 is there, there is a hit, 5 3 1, 4 is not there, so we replaced 5 4 3 1, again there is a hit. Okay, 4 3 1, again there is a page fault, so we replaced this 3 to 2. Okay, again there is a hit, 1 is there, 4 2 1, again there is a page fault, we just replaced 1 2 3, and again there is a hit, 4 2 3. So we use just mostly recently used, most recently used, this 3, or again among the pages which is recently used. the pages which will going to be swapping. Okay, so count down the page fault. Page fault is 1, 2, 3, 4, 5, 6, 7, 8, 9, and hit, number of hit 1, 2, 3, 4, 5. So this is all about most recently or MRU page replacement algorithm and Belady's anomaly. Okay, so see you in the next one. Thank you.